All right, so this is part D for homework 2, separations, and in this part, basically we're going to implement an iterative Rachford-Rice calculation to calculate the vapor-liquid equilibrium of the isopropanol water system that we used in part C, and explain how good guesses for the vapor fraction and liquid composition can be obtained from the dew and bubble pressure calculations, and we will also be checking our results for a described feed composition, and we will also compare with the binary VLE diagrams from part C. As I did in the previous part, I'm actually going to use the same Colab file as parts B and C. That way I can call upon functions I already wrote if I need to. And I'm just going to add this to the bottom. And I'll start coding from here. The first thing we want to do is make a function. So what we need to do is basically we're using the Rachford-Rice calculation that I derived in part A, but we need to take into account that this system is not ideal, so we are using the NRTL method. So we're going to do a flash, let me make sure I haven't used this as a title yet. I'll call this flash underscore NRTL. Our arguments are Z, P, and T. Z being the composition of the feed, P is our system pressure, T is our system temperature. We'll allow this to go through 100 iterations, and the tolerance will be relatively small. And essentially what this is going to do is it's going to solve for our phi, so our vapor over the feed, which is our vapor fraction, and then it's also going to solve for the liquid compositions as well as the vapor compositions. For the dew pressure, we're going to say dP and X dew, and we're pulling this from the dew pressure NRTL function that I defined in a previous part, and we just need Z and T here, and we also want to do so this was the dew pressure I should say, and we want to do the bubble pressure. And this is going to be our bubble P NRTL again, with the composition and temperature being provided. To check if we are in the two-phase region, we're going to look if the system pressure is greater than the bubble point, then we are in an all liquid zone, and if it's less than the dew pressure, we're in an all vapor zone. And as this says, we want to explain how good guesses for the vapor fraction and liquid composition can be obtained from the dew and bubble pressure calculations. So we want to start off with an initial guess for phi. Essentially, we need a good starting point, because if for some reason we were starting outside of like an acceptable value, so if we were outside of being between 0 and 1, we would have many errors in our calculation. As I mentioned in the previous video, at the bubble point, so when the system is at the bubble point, all of the system is in a liquid form, and so phi being the V over the F, we would have 0 as phi, and conversely at the dew point we would have almost all vapor, and so our phi would be equal to 1. And then to get our guess, we do linear interpolation between our bubble and dew points. So we kind of look at where our system pressure sits between the bubble and dew pressures and kind of guess phi based on those values. And then we use that phi to later scale and get a more accurate phi later on. So we want to start off with our guess for phi. We're going to set phi equal to the system pressure minus the bubble pressure divided by the dew pressure minus the bubble pressure. And that will give us our kind of interpolated guess for phi. And then we know the liquid composition should be equal to phi times the liquid composition at the dew point minus z plus z. What we're saying here is the liquid composition is equal to z when it is at the bubble point because of what I explained previously, and it is equal to x dew at the dew point, and this is doing a similar thing as up here. And now we want to iteratively solve for the actual phi. So for I in range n iterations that we define up here, we want to solve for our k values, which we're going to pull again from our properties, which I think I made PR, but if it's not, it'll let me know that there's an error. And actually, up here from the bubble P NRTL, I'm going to copy this. So this is what I need to calculate K, except I need to divide by the system pressure. And again, the system pressure is going to be given when we run the flash NRTL. We have to provide these three values, which we will do when we get to that point. And within this for loop, we're going to define our Rachford-Rice function. And we know that from the previous video, I believe it was part A that I did this, so I'm going to reference that. But I derived the Rachford-Rice summation equation. Then we are going to get the Rachford derivative, and that's going to be Jax.grad Rachford, and this is going to use our Jax automatic differentiation that we've been using. And we're going to reset this phi to optimize dot root scalar. We're doing our Rachford x0 is equal to phi. Our method is Newton. I won't go too much into this method specifically, but to use the Newton method, that is why we took the derivative of our Rachford equation there. And you could do the derivative yourself and just type it out here, but this is quite obviously a bit easier and faster. And this is where we're setting that, so f prime is equal to our Rachford derivative. And we want to take the root of this, and we want to get a new liquid composition. So we'll take the feed z composition, divide that by 1 plus phi times k minus 1. And then if we are below our tolerance, that's below our tolerance, then x equals x new, so we're setting our new x value there. And then we want to break out of the for loop. If we don't reach this by the time 100 iterations have gone by, then there's a problem, and it should let us know the code should spit out an error. And to make sure that this x updates, I'm going to put it again outside of this break. And I'm not sure if we have any errors in here right now, but to check that, I'm going to try to run it and see what happens. So that's really hard to read. Hopefully that looks horrible, but anyways, you get the picture. So we want to check our results for a feed composition of 25 mole percent isopropanol at 1 bar and 360 Kelvin. And what we want to do is we want to run this flash NRTL 0.25 isopropanol. Our pressure is 1 bar, so that's 1 e to the 5, 1 times 10 to the 5 pascals, and 360 Kelvin. And sorry, this is Z, so I actually need an array with the 0.25 mole isopropanol and then 0.75 moles of water. And I don't need this. That was just for specifying in the function itself. Again, I think I made a mistake that I made previously. I'm not sure if that was the only mistake, but I forgot this multiplication right here. And I'm kind of having to pause in between when I'm running the code because it took a while. So literally realized that I was just running all of this and not returning anything. So I need to return x and phi. I'll actually do that as phi, x, and y. So hopefully when I run this, it'll return our phi, our liquid composition, and our vapor composition. Another thing that I didn't do was I didn't define what y was, so we know that y is equal to k times x, and now it should be able to calculate y and give that to us, so that's why I was getting the y is not defined, because I was not telling it how to calculate y. Alright, this is our phi, so our vapor composition. This tells us that about at this point, about 57% of all of our material is in the vapor form. Right here is our X, or our liquid composition. The majority of it is water, which is not too surprising because we know that isopropanol is much more volatile than water. And down here is our Y, our vapor composition, and we still have more water because our initial feed was 75% water, so we can expect that. But there is a lot more isopropanol that is in the vapor than there was in the liquid, which makes sense. And now we want to check these values by comparing with the vapor-liquid equilibrium diagrams that I made in part C. So I'm going to take these so that I can reference them. What I did was I just commented out our phi, x, and y values so that I can more easily compare it to the graphs. But what we can see is at 1 bar, this is our TXY diagram. At 0.25, our feed for isopropanol, and 360 degrees Kelvin, you can easily tell that we are within the two-phase region, so we'll have some liquid and vapor. And obviously this is not exact, but if we kind of look here and go sideways at about 360 Kelvin, it's telling us that our liquid composition of isopropanol is about 0.05, and as you can see from our calculation that we did, that is true, so that checks out. That was our liquid, and if we do the same thing again, then we see with 360 Kelvin, again, this is not exact, I don't have all of the points on here, but in between 0.39 and 0.43, that is what our vapor composition is, and up here we calculated it to be 0.402, and so that is between those points, and so that also checks out. If you wanted to, you could add some lines to this plot to get more intersection points in order to check these values, but just visually checking, it seems like there's nothing that is obviously glaringly incorrect. And yeah, these 3 parts, I mean, this homework was 4 parts, but we had these 3 parts together. We covered the Rachford-Rice equation as well as the NRTL model, kind of getting into some more non-ideal situations. And I kind of went over everything that we went over in these 4 parts, but homework 3 will be out soon, so look forward to that. I don't remember if I said this already, but as always, thank you for watching.